Hello everyone, my name is Ayse. I'm a fourth year PhD student in Professor Zaltan Narcís group at Purdue. In this presentation, I will talk about our work on two-dimensional modeling of the crystallization of a commercial active pharmaceutical ingredient as a proof of concept study to show how this predictive tool can be used for design of experiments. Crystallization is the particle formation and purification step of active pharmaceutical ingredients in almost all the pharmaceutical processes. Here is depicted a typical tablet production process with the crystallization step highlighted to show its importance for us. Experience show that the properties of the crystals produced here affect the downstream processes such as filtration, milling, or tableting, and the bioavailability of the drugs. These properties, which can be the polymer size, shape, or morphology, are determined by the desired product attributes, and they also determine the process parameters. Therefore, we want to have tight control over crystallization and be able to drive the process as needed to ensure the crystal and eventually product quality. In this work, we focus on the prediction and control of the crystal size and shape as they highly affect the downstream processes for our specific commercial drug compound. For that purpose, here we propose and demonstrate a workflow to have a tool which will help to predict the crystal size and shape with changing process parameters and to optimize the process. This tool, as everyone calls it as digital twin nowadays, is aimed to assist people in exploiting the experimental design space without heavy experimentation. For developing a predictive tool here, we suggest a roadmap starting from getting to know your crystallization system and designing specific experiments that will train your model for its further use and optimization. In the first step, the preliminary and specifically designed experiments should give you the maximum information about crystallization mechanisms and the product variability with significantly changing process parameters, such as seeding point or temperature profile. The data from these experiments is used to construct a model with appropriate crystallization mechanisms for parameter estimation. Then, a couple more experiments are conducted to test the prediction of this model, and finally, if the model passes our test, it can be used for in silico design and experiments and optimization. In our work, we conducted several experiments in this shown setup by using inline process analytical technology tools and offline characterization techniques to acquire data for model training. We utilize all the PAT tools we have, such as UV for concentration, FPRM for crystal count, and PVM to detect the crystallization mechanisms during the experiments as inline tools. Offline tools were used for particle size and shape characterization, which were also included in our model training. The crystals of our commercial product, commercial API we have, so-called compound A, is shown here in two pictures. As seen, they form high aspect ratio crystals. On the left, you see the product crystals after several temperature cycling, while on the right, you see the crystals right after nucleation. It is apparent that they change size and shape significantly during the batch process, and our aim was to be able to predict their size and shape changes with changing process parameters. To train our model, we designed 6 different experiments with different temperature cycle number, seed loading, and batch time affecting the cooling and heating rates. These parameters were changed to have a diverse set of product crystals to have a predictive model. Temperature cycles were implemented because at least one is needed to match the bulk density requirements of this compound. Here is depicted how the temperature cycles work to eliminate small crystals and making them redeposit onto larger remaining ones, enhancing crystal growth and bulk density of our needle-like crystals. After experiments and deciding on the existing crystallization mechanisms, we developed a morphological population balance model of the crystallization system. 3 primary mechanisms were included based on experimental evidence. These are secondary nucleation, size-dependent growth, and size-dependent dissolution. The equations we used required 14 parameters to be estimated, which are highlighted in blue. An anomalous size-dependent growth formulation was developed and implemented in this work, which combines the behaviors of the 2 mostly used ones in the literature. This model is used in the parameter estimation calculations with shown constraints, such as length growth rate power being required to be larger than the width growth rate power, again based on our observations in the lab. In parameter estimation, our objective function was to minimize the difference between the experimental data and simulated data produced by by the shown model to find a parameter set. The experimental data used in the objective function are concentration coming from UV, cumulative crystal size distribution, and aspect ratio of the crystals coming from the offline characterization tools, and the total crystal count coming from FBRM. This last term corresponds to the crystal count, is another novelty of this work. It actually maximizes the correlation between the experimental crystal count and the simulated number density by using a polynomial fit between two. And it is beneficial for shrinking the parameter space during the search. On the left, the intercorrelation of growth parameters are shown and how the search space shrunk from blue to green with the addition of the fourth term, and on the right, similarly for nucleation parameters. For the crystal size and shape terms, we conducted a comparative study by using an optical microscope, Malvern's master sizer, and Malvern's morphology tools. With optical microscopy, we counted at least 250 crystals manually to obtain with length and aspect ratio data. Morphology has automated image analysis that can be fine-tuned based on the compound for acquiring the same data for thousands of crystals. Master sizer was used for size distribution since it is the standard method now used by industry due to its ease of use and fast and consistent data production. Two sets of crystals were used as benchmark. On the left, you see the standard particles with long dimensions and high aspect ratio, and on the right is depicted the crystals from calibration 3 experiment that were used for comparison due to their similar dimensions with much higher variation. Length and width distributions show that morphology with fine-tuning is the best option for aspect ratio calculations, and it is used during parameter estimation for aspect ratio formation. The size distribution from microscopy measurements were constructed from length and width information, while morphology automatically gives the size distribution. Here we decided on using master sizer for size distribution to stay relevant to industrial purposes, although the comparison of the size distributions show that significant broadening occurs in laser scattering technique. With these decisions, we finished the parameter estimation calculations by using 6 experiments and then used the model to simulate the extra 2 validation experiments. Here, the mean aspect ratio of the crystals is shown along with the D10, D50, and D90 values of all experiments. The comparison of model output and experimental data from validation experiments for the shape and size values were acceptable for our purposes, and we decided on using this model to show how it can be further used. First, we used the model to decide on the seed loading that will minimize the aspect ratio without decreasing the crystal size. We simulated 2 different scenarios that were modeled after the 2 calibration experiments with different temperature profiles as shown. For both experiments, it was demonstrated that the minimum aspect ratio with larger crystals could be obtained under 1% seed loading. The effects of temperature cycles on the crystal sizes could also be captured well. Secondly, we used the model to optimize the temperature profile to reduce the product aspect ratio for 2 different solution compositions. Here, the blue line shows the solution which is saturated at 75 degrees Celsius, while the red one is saturated at 70 degrees Celsius. The resulting optimum profiles are shown in the top right, which suggests a decrease from 4.2 to 3.9 in the aspect ratio of the crystals from the 75 degree case, and a decrease from 2.56 to 1.9 for the other. On the bottom plot, the concentration profiles throughout the batch time for both cases are shown on the phase diagram for further investigation of these scenarios. Here, these cases show how this digital twin can be used to optimize the process parameters and simulate the different scenarios. Finally, I would like to finish my talk by stating some conclusions. In this proof of concept study, we showed how to develop a morphological digital twin for a commercial drug compound to be used in silico design of experiments for size and shape investigation. I hope I could walk you through this process by explaining the systematic experimentation and computational work steps we have followed. Also, I would like to acknowledge my postdoc Boton, who is back in Hungary now for this work to be realizable. He has developed a software which is called crystallization that can do all these steps as long as the experimental data is provided by the user. This is a commercial software with a very user-friendly interface that is shown here. And as a part of my PhD study, I also followed his steps and developed a simpler one dimensional version exclusive for Takeda, who funded our project, and I'm hoping to agree with more to have 2D model in the near future. With that, I'd like to thank my advisor, Professor Naj, my postdoc Boton, and Justin and Charles from Takeda for all their support and guidance. And thank you for your attention.